Hi and welcome to the lesson of multivariable calculus. So in previous class, we discussed about equations of line in space. Now we are going to discuss equations of planes in space. So in the previous lesson, we talked about the equation of a plane that was x equals to 3, right? So this was the plane that was parallel to ZY plane. So we can draw it like this. X equals to 3 is this point, let's say, and the plane will look like this, right? At x, centered at x equals to 3. So like this. Okay, so it's stretched in the y direction and z direction, and it's fixed at x equals to 3. So this is the equation of plane that is parallel to yz plane. Now, in general, to find the equation of a plane, what we need is that if we have a plane, let's say this is a plane in XYZ coordinate system. So what we need is a vector that is normal to the plane. We will call it V, and a point on the plane, we will call it as P0. So the coordinates of P0 are X0, Y0, and Z0. And the vector that is normal to this plane, we will represent the coordinates as A, B, C. So for the equation of line, we needed a point on the line and a vector parallel to the line, right? So a point P0 and a vector V parallel to the line with the coordinates A, B, C. But in this case, for the equation of plane, we need a vector that is normal to the plane and a point line on the lying on the plane. Now, again, we know that the dot product of two vectors, that is A dot B, is equals to 0 if the vectors are perpendicular, right? Vectors are orthogonal, or we can say perpendicular. So now, using the definition of dot product, we can see that if I join this point with some other point, let's say P, any point on this plane with coordinates x, y, z, and then we know that since this vector V is perpendicular to the plane, therefore it is perpendicular to every line on the plane. Therefore, this vector is perpendicular to the vector, this vector P naught P, right? So the dot product of these two vectors should be equals to 0. Now, using this definition, we can find the equation of the plane. So P naught P, we know already it is nothing but it's P minus P naught. So it will be X minus X naught, Y minus Y naught, and Z minus Z naught. So this is P naught P, and vector V is A, B, C, right? Now the dot product of these two vectors is defined by this equation, that is ABC dot this vector, that is P naught P. So it's equals to 0. Now the dot product is taken as corresponding components are multiplied, and then we have to sum all these products, right? Plus C times Z minus Z naught equals to 0, where X naught, Y naught, Z naught is a point lying on the plane, and ABC is the vector that is normal to the plane. So this way we will get the equation of the plane, right? Now let's see an example finding the equation of a plane. Right now, see here, we are asked to find equation of the plane containing the point and normal vector. So we have a plane, right? We have a plane, and a point is given on the plane, that is 3, -3, and 2. So this is the point, let's call it P naught. This is the point, and a vector normal to the plane is given, that is 4, 2, 3. Now, by the definition of the equation of plane in space, we have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So a is given, it is 4x minus x naught is 3, plus b is 2, and y minus y naught is -3, so it will be y plus 3 plus c times z minus z naught, so z naught is 2. Now we simplify this expression, it will be 4x minus 12, 2y plus 6 plus 3z minus 6 equals 0. So further simplifying this equation, we will get this equation. So that is the equation of the plane. Now if we want to draw the plane, we need to find the x, y, and z intercepts of this plane, right? So the x-intercept is one where the y and z will be 0. So if I draw the three-dimensional space like this, x, y, and z, so the x-intercept where will be the point where the plane is cutting x-axis. So y and z are 0, therefore we will get 4x plus 2 times 0 plus 3 times 0 equals 12. So from here we get x equals to 3. So this is the point, x equals to 3 on x-axis. And for y-intercept, you know that x and z will be 0. So 4 times 0 plus 2y plus 3 times 0 equals 12. From here we get y equals 6. So let's say y equals 6 is this point. And for the z-intercept, x and y are 0. So we will get z equals 4. So the point z equals 4 is, let's say, here. Now we will join all these points to find the plane. So this is our plane. It's a triangular plane, and it's in the first octant. We can see that it is the first octant, right? So this is in the first octant. So this is the plane that is represented by this equation, 4x plus 2y plus 3z equals 12. All right, so next move on to the next example. Okay, so here now example 6, we have to find the equation of the plane containing the points PQR. So 3 points are given, and what we actually need is 1 point and a vector that is normal to the plane. So let's consider that we have a plane. Okay, we have a plane, for instance, like this. Okay, we have a plane and we are given 3 points on the plane. Let's say P, Q, and R. So this is point P, this is point Q, this is point R. Now we need to find a perpendicular vector that is perpendicular to this plane. So what we can do is we can just join these points. So let's say I'm joining these points from P to Q and P to R. Right now these vectors are on the plane. If I find the cross product of these two vectors, what I will get is I will get a normal vector pointing outward, pointing normal to the plane, right? I will get the normal vector. So PQ cross PR, the cross product of these two vectors will be a perpendicular vector to the plane. So I need to find PQ, that is Q minus P, and I need to find PR, that is R minus P. Right, so the points are given, we can just find PQ. So PQ is Q minus P, therefore we get -2, 5, and 1. And PR is this point, so it will be R minus P. So the components of R are 0, 1, 4, minus the components of P are 3, -1, 1. So 0 minus 3 is -3, 1 minus -1, it will be 2, and 4 minus 1, it's 3. So these are the components of PR, right? -3, 2, 3. So now we get these two vectors PQ, PR that lie on the plane, and now the cross product of these two vectors is going to be the normal vector to the plane. So the cross product is defined as the determinant of these two vectors. So is the determinant of these two vectors with the unit vector I, J, K, right? I, J, and K, and PQ will be in this row and PR will be in this row. So now just finding the determinant, we get the vector 13i 3j plus 11k. So it gives the vector that is normal to the plane. Now we have the vector that is normal to the plane. We have 3 points on the plane, and we can choose any point because all these points are on the plane. And with this vector, we can just find the equation of the plane, right? So we have the normal vector and we choose point P, let's say. So point P and the vector V, we have the point P is 3, -1, and 1. And vector V is nothing but 13, 3, and 11. Now just by definition, plugging in 3 times x minus 13 times a times, that is our a, b, and c, that is our x naught, y naught, and z naught, right? So let's call it p naught. So 13 into x minus 3 plus 3 into y plus 1 plus 11 times z minus 1. And by simplifying, we will get 13x plus 3y plus 11z equals 47. So this is the equation of the plane, right? And by finding the intercepts, we can easily draw this plane as just we draw it earlier in the previous example, right? Now let's see some more examples. Okay, there are no more examples here, so we can just have some practice problems from the exercise. Now the other topic is that parallel and orthogonal planes, right? So if two planes are parallel, it means that we already have idea of parallel lines. Like if these lines I can see, these are parallel lines, right? So these lines are parallel, so they did not intersect. And similarly, we have two planes parallel if they're normal vectors. The vectors normal to the planes are parallel, right? So we can check whether the planes are parallel or not by just checking that their normal vectors are parallel or not. And similarly for orthogonal planes, by orthogonality, we means that if two lines intersect at 90 degrees, we say that these two lines are perpendicular or orthogonal. Similarly, if these two planes intersect at 90 degrees, so we can say that these are orthogonal. So similarly, if the normal vectors of these two planes are orthogonal, implies that the planes are orthogonal. So we can check by using the dot product of these two normal vectors, right, of the plane. So if the dot product m dot n is 0, it implies that the planes are orthogonal, right? Now see an example. Find an equation of the plane containing the point and parallel to the plane defined by this equation. So we are given with a point containing two, let's say this is the plane, or just we can look at the figure given here. Let's say this is the plane, and a point is given on the plane that is 2, -1, 3, right? And the normal vector to this plane is not given, but the other information that is given is that the next plane, that is this plane, is parallel to this plane. Let's say it's plane A and it's plane B. So plane A is parallel to plane B, where the equation of plane B is given. So it's 2x minus 3y plus 4z equals 6, right? This is the equation of this plane. Now, if we are able to find the normal vector of this plane, plane B, then we know that since these planes are parallel, so this vector that we find here, that is normal to B, is also normal to plane A, because both planes are parallel. So their vectors will also be parallel. So if this is the normal vector of this plane, so it will be similarly normal to this plane also. So you can find the normal vector of this plane, plane B, from the given equation, because we know that the equation contains the normal vector. So if we go to the definition, we have ax minus x naught plus b y minus y naught plus c z minus z naught equals 0. And here we will get ax minus ax naught plus by minus by naught plus cz minus cz naught equals 0. So these a, b, and c associated with these x, y, z's are nothing but the normal vector a, b, c. So from here we can see a is 2, b is -3, and c is 4. So the vector that is normal to the plane B is 2, -3, and 4. Similarly, this vector is normal to the plane A as well, because both the planes are parallel. So we can use this vector with this point given, and we can find the equation of this plane A, right? Plane A. So let's see. Here it is solved. You can see that the normal vector is 2, -3, 4, and the point is given. This is the point. So using, we get this equation of the plane. All right. Okay. Now the angle between two planes. Now to find the angle between two planes, we can use the definition of the dot product, that is A dot B equals A B cos theta. All right. So the norm of AB, norm of A, norm of B with the cos theta. Right. So cos theta equals A dot B divided by the norm of A and norm of B. Okay, so now how to find this A and B? Now, since the planes are intersecting at some angle, theta, let's say here, so it means that if we are able to find the normal vectors to these two planes at the point of intersection or at the line of intersection, since the planes are intersecting on a line, because if two lines are intersecting, they intersect at a point, but if two planes are intersecting, they intersect on a line, right? Now, if we are able to find the normal vectors to both the planes on this intersection, then we can simply calculate the angle between these two planes, because the angle between these two normals will be the same as the angle between these two planes, right? So now the equation of plane is given in the example. Equation of both the planes is given. We can find the normal vectors. So since this is, call it plane A and plane B, so normal vector of plane A, we can find it from here. This is A, this is B, this is C, so it's 3, -1, and 2. And the normal vector of plane B, it is 2, 3, and -1. Now we can just apply the dot product here, NA dot NB divided by the norms of both the vectors, product of the norms, right? By this, we can just then take the inverse of this whole stuff and we'll get the angle between the planes. So it's solved here. You can see simply, just I am telling here how to take the dot product. We have already talked it earlier, but I am telling it again that 3, -1, 2, dot 2, 3, -1. So the dot product is multiplying the corresponding components. 3 times 2 is 6, and then adding all the products. So it's 1. Okay, and find the norm. Let's say find the norm of a vector NA. So it will be square root of the sum of squared components, right? So you will get it as square root of 14. Similarly for NB, we will also get it square root of 14, and then just by dividing with the dot product, by dividing the dot product with these two products, these two norms, we can just find the angle theta, right? And now move on to the next example. Okay, now find the parametric equation of line of intersection. Line of intersection of the planes defined by these. So the two planes are given. We have to find the line of intersection. So this is the line of intersection of two planes, right? This is the line of intersection. Now to find the line of intersection, we already know that to find the equation of line in space, we need a vector that is parallel to the line, right? And a point on the line. Okay, so first of all, to find the parallel vector, what we can do is we can take the normal vectors of the plane. So this is normal to P1, this is normal to P2, that is N2. Now if I find the cross product of both these vectors, since these both vectors are normal to their corresponding planes, so their cross product of these two vectors, it will lie on the line, because we know that the cross product of two vectors is a perpendicular vector on both the vectors, right? So if these two vectors cross product, we take, it will fall on the line, right? So by using the cross product, we will get this vector that is parallel to the line. Okay, so this vector falls on the line. It means it's parallel to the line because it's collinear to the line. And to find the point on this line, what we can do is, we know that if we have a line on XY coordinate system, then the line cuts through two points. It must cut through 2 points. Either it will pass through origin, or if it's not passing through origin, then it will cut on x-axis and y-axis, right? So the point where it cuts y-axis, the coordinate of x is 0. So it's like 0, b, and where it cuts x-axis, the y coordinate is 0, so it's like a, 0. Similarly, for a line in space, we can say that the line in this space is will be having some coordinates, like where x is 0, or where y is 0, or where z is 0, right? So there will be points. So we can do one thing, that we can set, let's say, z equals to 0. If the line is passing through xy plane, so the z coordinate will be 0 there, right? If it is on the y plane. So now if we put z equals to 0, so this component will be 0, this will be 0. We will have equation like this. So 3x minus y equals 1, and for the second plane we will have this equals 4. Now we have two equations with two unknowns, so we can find the xy coordinates. So xy points, we will get xy from here, and z is 0, since the points we get from here, let's say x is a and y is b, so we'll get this point on the line, right? So this will be a point on the line. And now we have the vector that is parallel to the line, that is the cross product of two normal vectors. Okay, this is v, and this is our point p naught. So using point and the normal vector, parallel vector to the line, we can easily find the equation of the line. What we need was a point on the line, right? A point on the line by setting z equals 0. And using with this z equals to 0 in equation of planes, we get a point on the line. And by using the cross product of these two normal vectors, that is n1 and n2, we just found the parallel vector to this line, right? The line of intersection. So this is how we can find the parametric equation of the line of intersection of two planes, right? Okay, so now the distance between 2 points on a plane. distance between a point and a plane. Distance between point and a plane. So we already know that distance between a point and a line in two-dimensional coordinate system, if this is a point A, B, C, and this is line y equals to mx plus c, we can find the distance between the point and this line. It is given by ax plus by plus c over square root of a square plus b square. And sorry, I should write it as x comma y. We have the point x comma y, and equation of the line. Okay, let me draw it again. For instance, we have a point and a line. This is a point x comma y, and this is line ax plus by plus c equals 0. Then to find the distance, perpendicular distance from this point to this line, we need this formula, right? Similarly, for three-dimensional case, again, we can use the same concept. So the formula now we get is this one. This is just the extended version, right? Okay, so this is just the extended version of that formula that we use in the two-dimensional system. So here we have square root of a square plus b square plus c square, where in that case we have ax plus by plus c over under root a squared plus b squared in 2D case, right? For the equation ax plus by plus c equals 0 and the point x comma y. All right, so we find the distance. In 3D case, this will be the formula. So it's negative d here because the equation given in this case is in the form of ax plus by plus cz equals to d. If we write it in this manner, plus d equals to 0, then in the formula it will be plus d, right? So it's the same thing, but here it's the d is moved to the right side, so d is constant, so it may be negative, it may be positive, but in general we can write in this way, right? Okay, so now this is an example. This is a point, this is a plane. So we have x equals -2, y equals 1, z equals 3, a equals this is a, so a is 2, b is 3, and c is 1, right? And d will be simply -1, because if we move it to the left side with the equation, it will be -1. We can use here in this formula, and we get the distance from the point to the plane, right? So this is all for the today's lecture. So it's the third lecture, and the next class, then we will proceed further, and we'll see some more examples about sketching the planes and sketching the graphs in 3D, right? So that's all for the time being. Thanks for watching the lesson.